Hi guys, in this video we are going to talk about Gauss's law, which is one of the most important laws in electrostatics. Let's start with the problem. Problem says, let's say we have a sphere which is uniformly charged and you have to find the value of electric field right at its center. Right over here, you have to find the value of electric field. You might say that answer is pretty simple. By intuition, it looks like that electric field must be 0. But what if I complicate the question a little bit and I ask you the electric field not at here but at some point outside the sphere? Then you can also say that problem is doable. I can take a small element dv which will have some charge dq equals a charge density into dv, and dv can be written as a product of dx, dy and dz. So this dq thing will be giving out electric field or a small amount of electric field in this direction, and if you take all of the elements and integrate the electric field over the whole volume, then you would get net electric field because of the sphere at this point. But how many of you are familiar with integration in 3 dimensions? Not many, right? So are we going to do it? No. Instead, we are going to learn a new trick which will ease our problems in finding out the electric field at various positions. So what is this Gauss law? Let me jump right into it and write the expression for the Gauss law. So expression of Gauss law goes something like this. Surface integration of E dot dA must give you total charge inside divided by epsilon naught. Now this expression might look intimidating to you, but don't let it scare you. It's not that difficult to understand this law. This is a very primitive law, and to ease your tension I can tell you that this law can be easily derived from Coulombs law. So how to go about understanding this thing? Let me start from the basics. So the story of electrostatics starts with this particular law that says some bodies have a property called charge. That property is represented by Q. So let's say this is Q and this is some other charge. I'll denote it by Q naught. So let's also make this as positive charge. Now this positive charge will get repelled by another positive charge by a force, which is what Coulombs law gives, and that is written as F equals K Q into Q naught upon distance between them whole squared, and as F is a vector, in which direction it will point? It will point in the direction of r cap. And what is this K? This K can also be written as 1 by 4 pi epsilon naught, and it has a magnitude of 9 into 10 to the power 9. So it's just a constant. Now what is electric field? Electric field is the area around a charge in which the presence of this charge can be felt. You can say that this charge Q is producing some electric field at this point, let's say E1, and some other electric field at this point E2. This value of electric field is given by KQ by r square, or you can also write it as 1 by 4 pi epsilon naught Q upon r square. That means if this thing is 1 meter away and this thing is 2 meters away, then you can say that electric field here will be 4 times as strong as electric field here. Now this point will be represented by an arrow like this. This arrow's direction represents that if you put a test charge, let's say you put another test charge Q naught here, this test charge will be pushed in this direction, and the length of this arrow represents how much magnitude it has. So that means, let's say if this is 1 centimeter long, this another arrow will be just 1/4 of a centimeter long. Then people had an idea that why not join all of these lines, and they joined them and we got something like this, and this is what we call as electric field lines. Now joining them solved the purpose, but we lost one information. Information we lost was strength of electric field. That is, we don't know whether this point is strong or whether this point is strong. Then another idea came into being, and we formed a quantity, or we defined a quantity called line density. And scientists argued that electric field is proportional to line density. And what is line density? Line density is basically number of lines per unit area. Electric field, as we know, has a pretty simple formula, 1 by 4 pi epsilon naught Q upon r square. What is this number of lines? Number of lines, you can take anything. The only thing is you have to be consistent about it. Always have to take 10 lines per coulomb or 20 lines for 20 coulombs. Scientists took a very weird value, and that value was 1 coulomb will give out 1 upon epsilon naught lines. Why only 1 by epsilon naught? Let's check this whole line density thing. If 1 coulomb is giving out 1 by epsilon naught, then Q coulombs will give out Q upon epsilon naught number of lines, and this is very important. Always remember, Q coulomb of charge gives out how many number of lines? Q by epsilon naught. If that is the case, you just plug in the value Q by epsilon naught, and upon area is 4 pi r square. That will be the area of the sphere. This number of field lines upon area is also giving out the same thing which electric field is giving. So line density gives us an idea that how much strong the electric field is. Closer the lines, more the electric field there will be. This gives an idea of flux. Flux is simply the name given to number of electric field lines passing through an area, and we'll denote it by a symbol phi. Phi is nothing but number of lines, so phi upon area, if you remember, was electric field. So phi is basically E into A, but there's something wrong here. It's not simple multiplication, it's dot product that is happening here. Why? Because this area is actually area perpendicular. As we see, if we make area like this, then all the electric field lines are going through it. But if we make area like this, then none of the electric field lines are moving through it. So orientation of the area matters. So what do we want to multiply with electric field to get the number of field lines passing through it is the perpendicular area. Here, if I calculate phi 1, that will be just E into area. But if I calculate phi here, that will be E A cos theta. So phi is not just E into A, but as a dot product, E vector dot A vector. A vector to any small surface is normal to the plane of the surface. E dot A also is only correct when electric field all over the area is just simply E, like in this case. But what about this case where electric field here is E1, here is E2? Then our only good friend to solve this kind of problem is integration. So we can say phi is nothing but, let's take a very small amount of area. There it will be E dot dA. At other point it will be E2 dot EA. But as it is a continuous thing, we will write it as integration of E dot dA. Now we have all the things in our pockets to understand what actually Gauss law says. Gauss's law says that flux passing through this must be equal to flux passing through this. Isn't it intuitive that number of lines passing through the surface S1 must be equal to number of field lines passing through surface S2? So if I write this phi 1, that must be equal to phi 2. How do I get phi 2? Phi 2 is pretty difficult to get because at each and every point electric field is different, and also it's not in the same direction as dA. So what do you need to do? You have to do it by integration. So E dot dA, and doing all over this yellow surface will give me the total number of electric field lines passing through the surface number 2. Surface number 1 is easier though, because first of all I don't need to do a dot product. Electric field lines are radial and area vector will also be radial. E and dA are in same direction. Dot product just gives us 1. Also the value of electric field all over this surface at every point in its surface is a constant, so we can take it out of integration. This becomes E integration of dA. How can I write electric field at this point? Electric field at that point is simply constant 1 by 4 pi epsilon naught into Q upon r square. dA integration of all the small dAs will give me area of this sphere, that is 4 pi r square. R square gets cancelled, 4 pi gets cancelled, and flux through 1 is Q by epsilon naught. So for this particular case, we can simply get Gauss's law. Phi 2 equals phi 1. Phi 1 is Q by epsilon naught, and phi 2 is integration of E dot dA. And both of them are saying this is the number of field lines passing through any of the surface. First one is good surface, second one is bad kind of surface. Now till now we have only seen the charges which are inside the Gaussian surface. This surface will be called as Gaussian surface. Now what if the charge is outside the Gaussian surface? Now flux or number of field lines passing through that surface because of an outside charge is, we say, is 0, because the number of field lines that are going in is exactly equal to number of field lines that are going out. Or mathematically you can say that at this point the area vector is pointing here, this point area vector is pointing here. So here E dot dA will come out to be positive, here E dot dA will come out to be negative, and that will happen with each and every electrical lines of forces, and that's why net lines or net flux that is because of the outside charge is always 0. Now what if I have a lot of charges inside the Gaussian surface? Let's say this is Q1, this is Q2, this is Q3. Let's write the outside surface as capital Q1 and capital Q2. So if I have to write the total flux on that surface, that will be equal to Q1, Q2, Q3, and also flux because of outside charges Q1, Q2. Now you already have seen that this is basically 0. If 1 coulomb of charge gives out 1 by epsilon naught lines of forces, Q1 will give Q1 by epsilon naught, Q2 will give out Q2 by epsilon naught, Q3 will give out Q3 by epsilon naught. So how many total lines of forces are passing through this? It's total Q in upon epsilon naught. And if you wanted to find it some other way, that is, let's say E1 into dA1, E2 into dA2, and then integrating all over the surface, then you can also say that is equal to E dot dA over that closed surface. Now Gauss law has numerous amount of application. Will not be able to cover all of that. We'll just use it in its most profound way, that is using it as a trick to find out electric field in some complicated situation. And we'll take one of the complicated situation which we started off this video with, and that was finding out the electric field because of a sphere. I have to find electric field at this point. Including this point, I can make any Gaussian surface I like. But what's my purpose? My purpose is to find electric field here. That will be E, but here electric field is E1, here the electric field is E2. Moreover, they are not even in sync with dA, so I have to take care of theta also. If I take this white surface as my Gaussian surface, I'm in a lot of trouble. So remember, Gauss law is only useful when there's only one thing to find out. That is, you should take the Gaussian surface such that electric field all over that surface is uniform. If I take a sphere of radius small r, I can argue that every point on that sphere will have same electric field. And how can I say that? It's just from rotational symmetry. That is, if I take this sphere and if I rotate it, there shouldn't be any change at the electric field of that Gaussian surface. Because of this, I'll take sphere as my Gaussian surface. Now if I take sphere as my Gaussian surface, let me write the Gauss law first. E dot dA equals Qn upon epsilon naught. Now let's simplify this. This circular E dot dA is simply E into dA because there is no cos theta involved. Qn upon epsilon naught, if this charge density is given, then you can write charge density into total volume, or if total charge is given, let's say capital Q, then you can simply write capital Q is the charge on that. Now as we know electric field is constant, we can easily take it out. Equals Q by epsilon naught, and integration of area again will give me 4 pi r square. It's the area of Gaussian surface. E equals 1 by 4 pi r square into Q by epsilon naught. And if you want to write it in another form, this is also kq by r square. So electric field, because a sphere resembles the electric field of a point charge. Point charge also gives us this. So a sphere can be replaced with a point charge with exactly having the same amount of charge, just kept at its center. And this insight was given by Gauss law. This is one of the many insights that are given by this very beautiful law. So I hope you have more idea about Gauss law than you started off this video with, and thank you for watching.